I can't make a co-host for some reason. Anyway, I think let's get started. So let me know if you. So I think I think this is the CS 229 lecture notes. Again, like you don't have to take a note of this right now. I'll share this again on the GitHub page and yeah. Uh, I think the meeting is getting recorded. Uh, yeah, I think it's getting recorded. Okay, cool. Let's get started. So let me give you some brief idea about what we are trying to do. And yeah, so the reason why I think this might be interesting to all of you is okay. Let me share a whiteboard with all of you. So we in machine learning, I think the kind of problems that you see, the most basic one of them. Oh, my voice is low. You can't hear me. Okay, maybe it's your problem. Something is maybe some configuration server is probably uh, off in your side. Maybe you can check. Yeah. Okay, so I think the kind of uh, place we should start is usually in machine learning. So there are two kinds of or three kinds of rather than machine learning problems. Does anybody know what are the three problems? What are the three kinds of machine learning problems? Or three kind of classification or category of machine learning problem? What are those three categories? So one is supervised learning. Which is the most common part. So supervised machine learning. Then the other two are unsupervised, uh, and the third one is called semi-supervised. This is I think a lot being talked about in recent time. It's also the same category where reinforcement learning falls into the category. Uh, so uh, so we'll start with supervised. We'll go at some unsupervised at some point, and then we'll also go to semi-supervised. If time permits, I think there will be some time to also go through that. But I want to start at a very basic level and talk to you guys about how some of the in most of the modeling problem you will have some data. So usually you will see so we'll be talking about supervised learning from now. So there is two things. One is X and Y, and X is your data, and this can be one feature. It can be multiple feature, and it can be also it can be right now it can be anything, text, you can have images, you can anything that you can convert to a numerical form is a feature that can be used by models. And then Y is your label. That means someone has and you have collected the data, and the label is guiding your model to learn that the relation between the feature X to the label Y. And almost everyone who I usually talk to, uh, they kind of have this notion that okay, how does so given this kind of setup that I have a X, which is my feature set, and Y. So most common paradigm that we can think of is we take some feature weights. So that means like if suppose like I have three features: age, height, and suppose
Yeah,
city,
एक
right?
20 वाला दे देना.
If I have three three parameters, and I can tell whether a person is healthy or not, right? I have a label like this, 1 or 0. So I think the most common way is that you add some feature weights, and you say that okay, I will multiply weight 1 with age plus weight 2 with height, plus weight 3 with city.
Yes,
And this might be very basic for all of you, right? I mean, a lot of people might have already. And I will try to create. I will try to learn a function which goes from, which is like, it's not a function like, I mean, when I multiply it, itself is a function. It's a linear function of this feature. But I will basically learn a function of age, height, and city. This is what I will learn, and basically this one is okay. Yeah. So this the weight one and weight two, weight three are basically the parameters, right? And how do we learn this parameter, right? So how do we learn? How do we actually learn estimate this parameter? This is usually the problem. That how do we learn this parameter? And almost everyone that I talk to, they say that okay, you will take y and then you will subtract it from f of if my x are my features, and then we'll take square of this, and f is a function of x and w, both are function, and basically this is my loss function, and then I will do gradient descent by dl dw, and I will get some estimation of this, and then what I will do, I will learn the weights by w plus w minus some learning rate into dl by dw, right? So this is the most common thing that I see, or when I ask people, this is the most common thing that they respond. How many of you know this setup? How many of you, just to understand, how many of you knows or understand this setup? Can I see a raise of hand? Or anyone who doesn't know this thing? I mean, it's great if you don't know as well. I mean, that's fine. I think most of the people who have gone through machine learning at some point will probably have seen this, right? So yeah, great. So with that, so this is our setup, right? So what we will do today is we will look at some of these problems and dive much deeper and say that how do we get this kind of loss function? Is this loss function something? So the natural question that a lot of people might ask, that why do I take a square loss, right? So this called a squared error or mean squared error. And then some of you might say, oh no, this is depending on the problem. I will in logistic regression, I will, or some classification problem. It's not a regression problem. So one of the things none of you said is that this was a classification problem, and actually I ended up doing a mean squared error, which is not true. In classification problem, we use a different kind of loss. You can use this loss, but it's not going to be very useful. The model will take more time to converge if at all it converges. So then the question is, like, the question that I'm asking is, what is the motivation, or where does this loss function actually comes from, right? Is this something that we assume? So there are two kind of schools, right? One is that I assume a loss function. A lot of textbook, if you study, they will say, oh, how do I create a loss? I can create a loss by taking, so most of the textbook, not most of the textbook, but a lot of textbooks that I have seen, a lot of blogs that I have seen, they say, okay, the loss is nothing but my actual value minus my predicted value. This is my loss, and is a function of this loss. I mean, this is basically a function of this. Now I can, the function can be y minus f of x squared. This is my function. The function can be y minus f of x, just the absolute value of this. So one property of this loss, that it has to be positive. This has to be positive. So this is one property of the loss. What happens if it is not positive? What will happen? Can someone tell me, like, if it is not always positive, then what is the problem? Is there any problem in that?
Sir, in gradient descent,
Yeah. Aman, you have any thoughts?
yes, sir. I am saying, sir,
Sorry, I
am I,
think you did. Can't hear you.
sir, am I audible?
Maybe you can type in the chat. I don't know whether I can. I think you can unmute yourself and speak. Yeah, I think you can unmute yourself. But anyone who, yeah, Namia, go ahead.
Yeah, so I think it needs to be positive in order to quantify the overall value, right? Because in case it's negative and then there's also positives, there's chances it can cancel out.
Do I
And
need to unmute people or is it? Sorry, I'm not very. No, it's not muted. Yeah,
can you hear me
but
now?
I can't hear you.
Um, not. Is it
Can
any
everyone
better?
hear Namia? Oh, that's interesting. Somehow. Okay. So, folks, if you are not speaking, please mute yourself. But I can't hear Namia for some reason. Anyways, uh, yeah. So I think most of the response that are here are correct. That that basically like if this is not positive, then one of the problem is that like when because it is actually a sum over a lot of the samples and and then that becomes like that becomes like it can cancel out each other and then the actual loss would be much lower than the true loss, right? So that's the problem. So then one thing that we observed, so this question led to one thing that um, usually your set consists of a lot of so the x will have a lot of samples. Usually in machine learning, we talks about millions of samples or at least tens of thousands of samples, not less than that. If anything is less than that, there it's very hard to kind of justify some of these models. Yeah, I mean people have done previously with thousand samples and things like that, but people don't trust a lot, or those models are not very trustable for various reasons. So one is that there is so when you are taking the loss, it is basically you're taking the y minus f of x, and this this function is averaged over multiple samples. Now the other thing that I might ask is that why should we take a sum? Like why should we take an average, right? Can I take a product of all of this? That still will be a loss, right? I can still take a product of all of these across all of these samples, and still that would be a loss, right? So one thing that I want to tell you that there's a lot of things. So I can actually come up with any function and I can also decide whether we can do product and we can do other combinations, but usually people don't do it. And why is that? That is the answer that we're trying to find, and it goes very deep into probability theory. It goes very deep into the assumptions of machine learning. This kind of setup. So one assumption that is always made in any of these problem is something called, so if you see that like you'll see a lot of papers, they will say it's a IID sample, right? So it is called identical and independently distributed sample. So in probability we call as two independent events. So two events are independent if the probability of each of the event are unrelated, right? That is so if I say what is the probability of you eating ice cream to kind of India winning a match yesterday, that probability is to somehow independent if you don't watch cricket. If you watch cricket, there might be, maybe India lost and you were sad, or India won and you were very happy, and you eat ice cream the next day. But in general, two events, if they are unrelated in nature, they don't, the probability of one event doesn't affect the probability of other, they're independent events. So in machine learning, the one thing in a lot of problem setup, not in some problem setup, this assumption is not necessarily true, but in a lot of problems, most of the supervised learning problems, you will this assumption is made that each of the samples are independent in nature. This is a very big assumption. So don't take this assumption very lightly, because if this assumption is violated, then there's a lot of problem. Then none of laws and all these things will work. Theoretically, none of them will work. So the reason why this independent assumption is very important, if you can only because like if two samples are dependent, right? Suppose like and I gave that example, right? So suppose like in that set, suppose like you are saying whether customer will buy something or they will not buy something, and in that setting, if I buy, maybe my friends also buy, right? So in that scenario, things are not independent truly, right? And that can lead to problem, right? So that can lead to problem because now you're, if there's some samples like that, the model can learn that pattern, and that can lead to because your assumptions then are wrong, and the model can learn that, and that can lead to noise. So that's one of the very big assumption. And they're also identical. What does identical means? That they're identically sampled, right? So there's no bias in your sampling. A lot of time you will see that when we go and and sample our data, we don't care about the bias. We say that, oh, I have taken a random sample, and that model is unbiased by that sense, right? So you will see in statistics there are a lot of ways to do stratification, saying that, okay, in that case, can I also like take a balanced sample? For example, suppose you're building this model in India, right? So we have city as a parameter. Now all of your data comes from the metro cities, right? Then none of the things comes from your second tier, third tier cities, or some of the maybe rural areas. You don't have any data, and now your model is definitely biased, right? So in that scenario, you try to you try to restrict your set or training set by collecting samples from different cities. Unless you do that, it is going to affect the accuracy or the trustability of your model. Now, some other person, suppose suppose a healthcare company is building this model, they can have a very different justification. They can say, hey, if I do stratified sampling, I will face one problem. So all these things are trade-off. There is no right answer to how to do this. You have to, when you are solving a problem, you have to think from the, from what you want, what is the right solution, and then you have to, do some of these assumptions or take or break some of these assumptions. So one of the things that a lot of companies are worried about is uh, suppose I have released an app. Suppose this whatever problem, like whether a person is healthy or not based on their age, height and weight, height, weight and city. This feature I have launched in my app, and my app is only used by metro cities. Now then, should I go and collect data from rural areas? That is a question. It's an open question. I don't know the answer to it. It will depend a lot what the performance of the model is. Because if I collect from rural areas, my model will not be correct on the user population that I care about, because there will be a lot of bias. Maybe it's not a lot of bias, but that can happen. So I just want all of you to be aware of it. Okay. So we'll now go to the lecture notes and try to make sense of them one by one. Uh, so we'll start with a very simple supervised classifier called KNN, or K nearest neighbor. So again, people who are joining late, please mute your mic so that your the other people don't hear echo. If you want to speak, please feel free to unmute and talk. So let me share my screen. Yeah, let me know if you can see my screen. I hope all of you can see my screen, right? Okay, great. So let's start here. Again, I have shared the link. You can also watch this video. These videos are very, very technical, and I like some of these videos. So this is the KNN algorithm, right? So and I hope all of you know the KNN algorithm. This is the most simplest algorithm. And so what does KNN does? So KNN does very simple thing. It is saying that if I suppose I have a training data, I have some training data, and I collect the training data, right? So and for each of these, I have some labels already. So I can store this, right? And how can I store this? I can store this in a dictionary, saying that for each of the my ID, I have this XY tuple, right? I can store this in a dictionary. So what I can do, so given a new point, given a test point, I can go through my dictionary, each of my dictionary entry, and I can define a function saying that x text versus this x that I have, right? So and what this function would say, what this function can mean two things. One is either it can be similarity or it can be dissimilarity. Both are the same thing. Similarity is just one minus dissimilarity or something like that. You can actually write it. So I will do this, right? So if I do this, then for each of this dictionary entry, I will have, so now my dictionary entry might be, okay, now my dictionary entry would be that, I, then, X, then Y, and then some score, maybe some distance score, some distance, right? So distance that would be there. Now I can sort this dictionary entry for X test. I can sort this, and then I can pick the most closest, most closest K points, right? So I can do that. And then I can look up what their labels are. That second is I look up what their labels are. And third is that I do a majority voting, right? So if all of these are like, so suppose like I choose K equal to 5. If, 3 of them are blue and 2 of them are red, then I say it's belong to this blue class, right? So these are extremely, simple classifier. All you need to do is have this dictionary and have a function, and then you are done, right? So that is, so and you can actually, say that this classifier is quite good actually. I mean, it's not a very bad classifier in a lot of scenarios. Actually, it is used in a lot of companies today, as like once you have very good, so if your features are very good, then this can work, wonders, right? It's a very simple classifier. um, Now the question, is that how do I define the distance? The question here is not about the classifier, but how do I define the distance? And whatever you define the distance will actually matter a lot. So there are some good choices of, distance. So usually this called, this mean Minkowski distance is also called the P norm. So these I think the most followed, and you can, most of the time we choose P equal to 1 or P equal to 2. Most of the time people will use P equal to 2, or they will use cosine, right? But my intention here is not to cover this, but to cover one very fundamental principle in machine learning, which is called curse of dimensionality. And so one thing that uh, we should understand is, so I'll go to this curse of dimensionality directly. One of the things that all of you should understand is today we are in a deep learning world where our features are very large. It can be, millions of dimensions. And one of the problem for that is this curse of dimensionality. That is true for any machine learning models. And you have to be very kind of aware, or very mindful in dealing with machine learning problems when talking about this kind of curse of dimensionality. So why does curse of dimensionality happen? So the curse of dimensionality happens because of, this simple thing, that if I look at this distance function, the formulation of this distance function, is if you just look at this function, you'll realize that this is the reason why, cursor dimensionality happen. It is a fundamental, fundamental kind of a, principle why it would happen, and there's no way to avoid it right now. So other than you reduce the number of dimensions. So let's look at this, right? So what I'm trying to do, like, so suppose like I have my features are two-dimensional in nature. That means I have a y, I have a x, and I have 2 points in this dimension. So point 1 is suppose x1, y1. Point 2 is x2, y2. And usually the distance between these 2 points is nothing but square root of x1 minus x2 square plus y1 minus y2 square, right? This is called, this is the usual distance that, or this is the L2 distance that, this is also called Euclidean distance. You can also take x1 minus x2, this, mod of this, plus y1 minus y2. Absolute value of this you can also take. This is L1 distance. This is also called Manhattan distance. But whatever you do, now if I somehow add a third dimension, there will be an extra z term, right? So for any of this loss function, if I add a third dimension. So as I keep on adding this dimension, you will see I am just keep on adding positive value. So as my dimension increases, that means the distance, the value of the distance becoming larger and larger, right? The other way to think about it is like, if you have two dimension, then there is very little, space for fit, points. But if you have larger dimension, as you get the dimension get bigger and bigger, the points have much more area to spread across. What is the problem there, right? The problem is if the distance keeps on increasing, and if I have a lot of dimension, then my distance, the overall distance increases. And the problem is then that, it is very hard to define similarity and dissimilarity, because any random, it can, the points might be so far apart that any random points might seems like, closer, because like that's the problem that you are seeing, right? So you as the dimension increases, your problem of similarity or detecting similar points is becoming very harder. And that we have to be very mindful. So and this is an indirect relation why if we add more features, there is a chance of a lot more noise, right? In that basically this overfitting kind of happens. This is a slight intuition into overfitting, say that if you keep on adding features without thinking, the curse of dimensionality will set in. Although there's mathematically, mathematically you can actually relate, because we'll go to regularization, and then you will see. But this is something that is very important, and I wanted all of you to understand this. Any question on this before we move on to the actual topic of today's class? Any question on this one?
Hello.
Yeah.
Sir, I'm asking that in Kn and neighbor, basically the loss function is the distance value or something else?
Yeah, I think I mean, basically, like your error is nothing but how far apart you are from
Yes,
the
sir.
points, right? So it is I would say it is not individual distance, but average distance over the k nearest neighbor, right?
Okay,
So
sir.
in k nearest neighbor, suppose like I have a point which has all the neighbors very far apart, right? Right, the loss in this point is much higher than someone which is suppose like all the points are very close to each other, right? Then the loss is much lower, right? So I will always prefer this one rather than this one, right? So you can actually look at the loss and say again what is, but again the problem here is that this is not problem here, but problem in any kind of case, you will not be able to understand what the actual value of the loss is, right? So like a lot of people, so we can only look at loss in a relative term. We cannot look loss at absolute term, right? Suppose like you see, so I tell you the loss for my model is 100. Absolutely, this doesn't make any sense. I don't know whether the model is good or bad from this. But if I have another model where the loss is 50, then I know this model is probably better than this model, right? So loss is always relative in nature. In any case, you measure loss, it is an absolute sense, it will not be very useful. Okay, so that's kind of the first thing that I wanted to cover. So moving on to the next thing. So let me go. This. So I'll go through this lecture notes and clear the screen. So the the setup here is very simple, right? So we start with a very simple regression problem. You see that like I have only one feature, which is like the living area, and from there I'm trying to predict the price, right? So this and this is a plot of the data that again, like this is so we'll see that in all of machine learning, we make this assumption that we have this pair, right? One is as I said, the training example is basically a pair where you have the feature and you have the label. In this case, we have only one feature, and it is a right setup to start with. And then, as I said, that so what we are trying to do is that we are saying that we have this training set, we have this feature, and we have a learning algorithm, and that is my hypothesis. H is my hypothesis, and basically I pass this all this feature or one feature through this hypothesis or my algorithm, and it predicts some value, which is the value that I want. And then if depending on whether y is a continuous value or a discrete value, I can either choose regression or classification, and from there I will go, right. So again, like coming to linear regression, I think that the most simple, example, um, and what the premise is that okay, I have multiple features and I'm predicting the price, and this might be all like kind of something that you already know, that the setup is that okay, my classifier, that means my h of x, and you'll see the notation is very important. It is parameterized, h of x parameterized by theta. That means the parameters of these functions are theta, which are nothing but the w's that I'm talking about, and this basically a linear combination or linear weighting of my feature. And we will come into the why I stressed upon this parameter. This is parameterized by theta. I'll come into later why I'm stressing on this a parameter and not something else. We'll come to another setting where this is not a parameter and this is something else, and there we have very different assumptions. So in machine learning there are two ways of modeling a problem. All of you might have heard generative AI, right? The whole term of generative comes from a very classical principle in machine learning, which is called generative models. uh, there's two kind of model. One is called the generative model and another is called a discriminative model. uh, uh, has anybody heard about a discriminative versus generative model? What is the
No,
difference
sir.
between discriminative? What is a discriminative versus generative framework?
No, sir.
Okay. Okay, great. So I think then the fun starts from here. So great.
No,
So
I would
let's
like to take a shot at the answer.
sure. Go ahead. Go ahead.
Yeah, I had read this some time back. So discriminative, so basically we have a training data, right? And the discriminative would do that it has some training, it has been trained on a data, and
Mhm.
based on the training data, it would make some predictions on those training
Mhm.
data, and its answers will be based on only those training data, right? And it
Mhm.
won't be able to have, if we have something outside the scope of that training data, the model is not in the capacity to return a
No,
correct answer.
that is not the right direction, I think. So okay, so maybe you can add in after I explain it. I think you're not going the right direction. Uh, both of the frameworks are capable of predicting on value not in the training data. There is no difference in that. I'll come to that maybe then. Okay. Yeah. Sorry to cut you off, but because you're going the not the right direction, maybe I'll propose it and then we can discuss. So again, like I think we have already covered it, that we say that okay, h of x is nothing but this and you see this notation right now previously we had this notation and now we are going to this vector notation. This vector notation is very very important, by the way. Doing this one means running a for loop. Doing this one means calling numpy dot. These two are two very different, implementation, and this implementation is always faster, right? So be very mindful of that. That like I should not say always faster, but like if you have the right setup, it is generally faster. Vectorization operation are generally faster, right? So then we have this loss function which we discussed. Again, like here my classifier or my algorithm is h and it is parameterized by theta, and when I input x it gives me a y predicted, and then I do y minus y predicted, and here I'm choosing something which is called a mean square loss, or this also called the ordinary least square. You will see ordinary OLS as one of the examples, right? So with that setting, let's look at this algorithm, and this algorithm is something that we already discussed about, that okay, if I have theta, then I can do a gradient descent on top of it. So does anyone know why do we do gradient descent? Is there any intuitive sense why should gradient descent work?
Yes, sir.
Yeah.
Sir, in
Okay.
gradient descent, basically we are finding a point of gradient
Mhm.
in a optimal position such that we get a point for low bias and low variance.
No, but why would I take the gradient, right? Is there any reason to take the gradient?
Uh, yes,
So
actually, so
gradient.
Okay, maybe one by one, raise your hand. Otherwise, like
mm,
everyone is speaking at the same time. Yeah.
Okay, I'll go. So basically, with gradient, what we're trying to find is a point of extremity. Basically, in our case, it would be a minima. So what gradient does is finding gradient helps us find that point where the slope of that curve would be zero. So it would help us find an extremity value, which is our
Right. I agree that if I am at an extrema, or like I am at a maxima or a minima, or even like at a there can be other points as well where the gradient is zero. I will have some sense that uh, that whether this point is a maximum or minimum, right, or at least a local maximum or minimum. But that doesn't justify why should gradient take me to that point, right? You are saying if I run a gradient, I will know whether I've reached my destination or not, right? But I'm saying that doesn't mean that if you take the gradient, you will you will reach that destination, right? But what is the what is the reason? So these are very very fundamental question I'm asking. So if you don't
So
know the
can
answer,
I
that's
try?
fine. Yeah, go ahead.
Yeah, so I mean, gradient actually gives the direction where the function will go maxima. That's why we take negative, because that will give the direction where the error loss will be the minima. I mean, that's why we are using gradient descent, because you will come to know at which point the loss function will decrease.
Okay, so okay, yeah, I think all of you are correct, but you're beating around the bush, right? You're not actually talking about why. You are talking about this is what happens. All of you, do you see that that this comes from a very fundamental assumption that the loss you have is a convex function. So this will not happen to everything, by the way. If you have any mathematical function, you take the gradient, you will not reach maximum minimum. Don't be that is not a fundamental property of any mathematical function. Only if that function is a convex function. What is a convex function? Does anyone know what's a convex function? You see a lot
It's
of
like a parabola, like a cup. I can't tell the
parabola is
property.
one kind of convex function. It's not always like this. There are other ways. But the usual
If I draw a tangent, then the curve is on one side, something like that.
So there are two ways to define a convex function. So one very simple way is any 2 point, right? If you draw a line between any 2 point in that function, it will be always contained in that function, right? So suppose like I have a function like this. There is 2 point. I draw a line. It goes outside this. This is not a convex function. This is a convex function because take any 2 point, right, and draw a line between that. It will always be continuous. It will not go outside. If you do this, till infinity, the same thing will happen. This is one of the fundamental property of convex. Only in convex function, when I take a point and I take a gradient, it goes to the minimum. So the reason why your model gets stuck in local minima is not because of that there is a property, because it is not a convex function. I mean the data that we have has multiple assumptions that has been broken, and the loss is no longer a convex function, and hence you're getting stuck in the local minima. It's not because of other reasons, right? So that's I think one of the fundamental rule. Don't get it. So only in this kind of scenario. So that's why you'll see a lot of textbook will take out this parabola as example and say that okay, this kind of function you take, you're at a point, and actually so why they call it why they draw a parabola is because the loss is like a parabola, right? Because you have the loss is a function of square, right? Y equal to x square, sorry, x equal to y square. This is basically a parabola. Uh, so that's the reason, right? So you can now I hope you guys can all connect that dot, right? That okay, why is something why so all of this is coming from very fundamental assumptions, right? These are not like out of thin air. No one has said, oh, this has to be there. Yeah. Yeah. So basically, yeah, that's correct. Yeah. So I think that convex function is very big assumption, and it's not always true, by the way. Sometimes it is not true as well. But still we go ahead. That's fine. I mean, we know that there are some problems, but we make assumptions and then we go ahead. So only in kind of construction this happens, and then we have this loss, and then now we have the loss, and then then we can so basically we multiply. So this is my loss, and then I take take a small step in that direction. And then I will say, okay, yeah, great. Like my my theta is getting updated. So this I do for every theta. That means every parameter I have to do this, right? I have to take the gradient, the partial derivative of that with respect to my loss function, and then I get to this point, right? So then I update this, and then this is how it looks like. So this is why so you see that there are a lot of this this function is there, and usually you start at this point and slowly you kind of trickle down to the optimal points, right? Um, so right, so and this and there are two kinds of gradient descent. One is called a stochastic gradient descent, one is called batch gradient descent, and one is called the full gradient descent. So stochastic gradient descent is basically, so in my training set I might have 10,000 points, right? The actual gradient, the gradient descent that we are talking about, the in that algorithm, you only update the parameter after you calculate gradient for each and every point and take an average over it. So you take the gradient over each and every point and take average of them, then you take step, right? But in case of stochastic gradient descent, you take every point and you take a step for that point. What is the trade-off? Why do we? What are the difference? Can someone tell me, like, why one is chosen over the other? When will you choose one over the other? This is a very favorite interview question for a lot of companies. Why would one choose stochastic versus the full gradient descent or the random descent, or vice versa?
So to
full
find
gradient
so to find the
Raise your
minimum
hand and then like have the discipline. Sorry. Yeah. Go ahead.
so to find the minimum bias and variance point, we use the trade-off.
Okay. How about you, Namia?
I actually raised my hand sometime back. So
Okay. Okay.
what I wanted to ask was, so the whole idea of choosing a loss function would be based on the convexity of nature of the function, right? Is it right to say that we are looking for such functions when we are trying
Yes.
to pick a
Correct.
function?
Yeah.
Okay.
Yeah.
got it.
So usually we'll choose a convex loss function. That's why you can't take log. You'll never
Right.
see log in a loss function.
Right. Got it.
I don't know why. I mean, we should ask, like, why should I? So like and this is where I would say that this is where the inquisitiveness or take your so train a model, throw in any function, and see whether it converges or not. You will see it, like there is some problem. Maybe it will learn. Maybe sometimes it will learn. And some of the, so if you go and read some of the papers in 2000, that era where people are actually trying the lot of loss function, in some of the problems you'll be very surprised that they're using very custom loss, because the squared loss or the kind of we'll come to cross entropy. So those laws actually doesn't work for them. And actually, there's a lot of problem with squared loss and cross entropy loss. There's something called focal loss. You'll see this very used in deep learning, focal loss. And that is used often, right? So I'd say that the choice of loss function is not trivial. It needs to be very well thought out process. Most of the time we assume it's there. Okay, nobody cares, but it can actually lead to a lot of things. I'm sorry, someone was trying to explain.
Actually, even I had a doubt, so I had raised my hand on similar
Yeah.
question only as Navya.
Sure.
So, so we don't use log as for loss function. Like we have log loss and all, right?
Yeah, you are right. So we'll come to log loss, but we'll come to that. So I think there is a way in which you can convert log to also convex function.
Okay, so
If I
that means
remember correctly, yeah.
necessarily the loss function has to be convex. Only then we proceed, right? That's
Yes. I mean, if you are not, see here there is a trade-off, right? And here there is a difference with classical, a lot of statistical learning. So if you look at it, they are very uh, or there's a difference between computer scientists trying to do machine learning. Should not generalize, but there are two philosophies. One philosophy is so if you go to a bank or any regulatory framework where they are working with some of this linear regression and some of this model, they have to abide by all of these assumptions. And so in that case, if you introduce something which is not following the assumptions, then there's a problem. Does that mean the model will not learn? No, the model can still learn. So if the convexity assumption is not true, the model can still learn. But the thing is, a guarantee of convergence or the guarantee of certain properties of the model is no longer true. So you can't guarantee those things then. You can't say, okay, this is going to be, true, right? So that is a trade-off. So you can still define your loss function. It can be non-convex, but you have to understand now gradient descent might not work. But that doesn't mean it should not. It might not. You can look at the loss. The loss is coming down. It comes down a lot, and then it converges. Yes, great. I mean, if you see the loss getting stuck and in model is not learning, it's an empirical science to some people. Some people it has to be a lot more theoretical. So it's a choice. Yeah, I see a lot of raised hand. Yeah. Aman Prakash, you have a question.
Yes, sir. Yes. So I was talking about full gradient descent would take much longer time to converge as compared to SGD. So, but SGD would get a bad metric as compared to full gradient descent.
I don't think that's true. Both of these will get comparable results. You're right in the first point that to move the needle, that means like to update your theta, you have to wait along for the full gradient descent. Because why? You have to pass your parameters through all of, like, you have to update all of your, like, go through all of the training sample, then you can update your parameter. In stochastic, you can update it every point. So that makes it faster, right? So that way you can update your parameter faster. Whether so in that sense, you there might be scenarios where you reach convergence faster. You can't guarantee that one will lead to faster convergence over the other. You're just saying that I can move faster in that. I can make some changes faster in that. Maybe it will lead to convergence faster. Maybe it will not. The performance wise, I don't think both of them will lead to much difference. Yes, there's a lot of overfitting and all these things that are there, but there are ways to tackle that. They're not fundamentally true. That means that if you use one or the other, it's not fundamentally that one will overfit, one will not. You can have mechanism to stop that. So the reason why stochastic gradient descent is used a lot in deep learning is because in deep learning you have a lot of samples. So you wait for million sample to update your parameter, it will take a long time. But that being said, stochastic gradient is much more unstable because you're just looking at one sample and updating it. So your parameter updates will be much unstable, right? You will see a lot of oscillations, like losses going this way, that way, and then, but in so that is, I think, one of the a problem of stochastic gradient descent, that there's a lot of fluctuation in the model updates before the model update converges, right? So that's, I think, one point. Yeah, Anita, you have a question?
Yeah, so this is actually regarding the loss function. So you mentioned that, it has to be a convex function, which means your loss function has to be quadratic, right? Because only for quadratic your
Quadratic
loss
is
function.
one loss function. There are other convex loss function. There's a lot of other convex function as well.
Oh, okay. It's not just quadratic. Okay, sorry, that was my assumption. Because my question was, what about for other loss functions which are not quadratic? But then, yeah, I guess that answers
Yeah,
it.
there are other.
Okay, thank
Yeah,
you.
Hina, in terms of model learning, incremental. In terms of incremental data, yeah, you can use stochastic gradients. Yeah, I think Aman, you have a question?
Yes, sir. Sir, I'm asking that basically from how we will have come to know that which gradient descent should we use, stochastic gradient descent or gradient descent or full gradient descent.
As I said, if you have a lot of data, it becomes very difficult for you to wait, right? So in that case, stochastic gradient descent or batch gradient descent is the right way. If you see all neural networks, they have so many, deep learning, there's so many parameters and you have so many, data points. If you have to wait for all of this, so that becomes a natural choice. In all of classical, machine learning, people used to do gradient descent, the full gradient descent. Yeah. Orko, I think there are a lot of questions, so I'll make some progress and then I'll take your question maybe later. Uh, so yeah, so that's kind of the assumption, right? So okay, so I think we are at a point where we have the basics, everything basic setup. Now I would just go back and ask you this question that um, a lot of you have probably taken probability courses, and let me go back to the yeah. So suppose I have a coin. Suppose I have a coin, and this and we'll slowly go uh, to the assumptions of some of this model. Suppose I have a lot of coins, right? So head, I toss a coin, I get head, tail, and all these things. Now I ask you, what is the probability of head? How will you determine this probability of head?
Like
Total number
if
of
we
times we
toss,
got head upon the total number of occurrences.
Okay. So can I say n of h plus n of tails? Is that right?
Yes.
Okay. Um, now my question is like, suppose you get all tails, then what is your probability of it? Suppose I have 100 observation. What is my probability of it in this case?
If all are tails, then the probability will be 0.
0, right? But I'm asking you, is this true? Is this a right estimation then? That if I have all of them 0, is the probability of head really 0?
I mean, the number of samples are less, so it is not right not to tell like this.
Yeah, I mean, that's right. I mean, but you have just 100 data points, and you have to only deal with that 100 data points. Then what do we do?
But
This
in
is one
this
of the
case,
problems
as you
where,
mentioned,
yeah, sorry, go ahead.
uh, as in this case, as you mentioned that all are tails, so the probability of head, as the probability of head is 0, then the probability of getting a tail would be 1. So if
Yeah,
it
but
is
that's not true, right? I mean, the probability of head is not actually 0. Just because you saw 100 data point with 0, heads in that. So one of the point is that, okay, yeah, I have less samples. Then one solution might be, oh, let me go and collect more data. And if I collect more data, maybe I'll fix this problem, right? But so you see that there is one direction which is saying, let me collect more and more data, and over time my estimation will converge, right? And there is also another school of thoughts that will come into the picture, and so this is the fundamental principle of modeling, right? So of a lot of this estimation and all these things is a very fundamental assumption, and so even how do we get here is a important question, right? So we say that we take this like this is an average or something like that. So there is a lot of there's a lot of kind of debate around how do we get here, or actually whether we the thing that we're looking at, is that even possible. This you might be thinking, okay, these are very bad example, but it's not actually a bad example. I mean, if you think about it, today we have millions of words in a document, right? And suppose instead of head and tails, suppose this like these are this so when we talk about head and tails, these are binomial distribution. It can be a multinomial distribution. That means instead of head and tail, I can have different phases of a dice, right? Then I'll have 1, 2, 3, 4, 5, 6. That means there can be multiple classes, right? So think about today's words, right? So there's a huge corpus, and you have multiple words, and how do you get the probability of a dice phase? Suppose that what is the probability of one in a dice? You will say, okay, let me see how many times one occurred in the dice by the total number of trials maybe, right? Total number of trials. So that's how I'll estimate probability of 1 to probability of 6. Basically, number of times 6 occurred by total number of trials, right? Similarly, if any corpus is given, I will say probability of a word is nothing but the number of times a word occurred by total number of words. And now what you're saying is that just because a word has not occurred in a document, the probability of that word is 0. That is extremely unreasonable. And that can lead to a lot of problems, right? And the way people go around is that they will say there's something called smoothing. If you look up this word, there's something called smoothing, and smoothing is used. Then what you do is that you can say that, okay, like, let me add something which is extremely small, and doesn't move anything, so I will add a very small value both in the numerator and denominator, to kind of balance this out, saying that, okay, I will add something, in the denominator I will add 1, and in the numerator I'll add something like very, very small, and then the probability of that word, a word that is not in your document, will not be 0, but it will be a very small value. How what value is decided and things like that, you can calculate that. There's a whole kind of class of research into smoothing techniques and things like that, right? So my here then there's two kind of principle in machine learning. One principle says the probab so my what I'm trying to estimate is, so I have some data, and let's call that data as t, and I have some parameters, right? And what I will do, I will look at the data to estimate this parameter, right? So this whole probability distribution is parameterized by theta. I said when we're discussing that H was parameterized by theta, right? So this is one assumption, and in the assumption that we said, you can say, okay, if the way I can model this is basically n of head, but n of head choose plus n of tails choose n of h, then probability of to the power n of h, 1 minus probability to the power 1 minus n of h, right? And probability is nothing but your theta. So you want to estimate theta. So I'm saying theta is my variable here. So total number of toss, choose total number of head, theta to the power number of head, and 1 minus theta to the power 1 minus number of head. Can someone tell me what distribution is this from this PDF? What is the distribution?
Binomial.
Sorry, yeah. So it's a probability mass function, not this density, because it's a discrete one. But so then once you get this, then what I can say is that, okay, I have probability, d parameterized by theta is nothing but whatever n choose h, and theta to the power h, 1 minus theta to the power 1 minus h, right? And now I have multiple points. So what I can do is that I can get probability of d1 parameters by theta, is a product over 1 to n. If I have n points, I have that many products, and then this is called the likelihood function. This is called the likelihood function, and because it's a product, no one likes a product. So what we do is that we take a log of this, then this becomes a log likelihood. Okay, and if I take log of this, then I don't like writing all this math in the so let me go to the lecture notes, and I think we have all of this computed there. So let me go to the lecture notes. So yeah, so I'm talking about this one. So we said that if I had 4 out of 10 as heads, then the probability is 0.4. So what maximum likelihood saying that I am modeling this as P D given theta. So I want to be very, very careful here. This is not actually P D given theta. So usually D given theta means a conditional distribution. The way to think about this is P D parameterized by theta. There's a very big distinction between these two, and I think a lot of textbook do this, that doesn't differentiate. You say, oh, okay, what is a big deal? There's a lot of big deal actually. The reason is that when I say PD given theta, this theta becomes actually random variable. It becomes, so, and in this case, it's not a random variable, it's a parameter. So there's a difference. So when I say that, h of theta is a parameter, I'm treating that as a parameter. It's not a random variable. If it's a random variable, there has to be a distribution on top of it, and there's a different estimation technique for that. We'll come to that. But the first thing is very simple, that I'm saying that this is this this parameterized, and then what I can do is that I can, so this is called the maximum likelihood principle. This is my likelihood. This is my likelihood function, and I'm saying whatever theta gives my maximizes this function, that is the theta that I should choose, right? So this, oh no, we are moving. So think about this. So here we're talking about maximization, not minimization, because it's not loss. So I'm saying the probability of head, right? So that is my likelihood, the likelihood of the head. That's what I'm trying to maximize, that, right? Whichever theta gives me that this likelihood, that theta is the right theta, right? So I want to maximize. I find that theta which maximizes this likelihood, right? So this is called the maximum likelihood principle, and or likelihood estimation. And all you can do is that you want to do this, so you have this one, and then you can take the log. Usually, like, taking the log of the likelihood and the likelihood, they're same. They're kind of in similar direction. So you can take the log and make this product into a sum, and then we have this kind of a relation. And then you take derivative with respect to theta, and then you get your estimate. So whatever you said your estimate is from empirical value is not something that we reach by accident. Is actually backed by theory, that if you take this maximum, we actually reach that same point, right? So Emily is giving you that okay, what everything is empirical in nature, right? So whatever you're getting is from the data, right? So and Emily works if n is large, right? So if n is large, then only this estimation will be correct. Otherwise, this estimation may be biased, right? So if n is small, then there is a high chance that this overfit, right? Right. So like, and usually we'll see, like, if the bias, this is an unbiased coin, and somehow we see that like, so what you can do is that to solve that problem, right? So you will always add m. So to solve this problem, to make sure that it doesn't go to 0, you will throw like a value, so that if this is 0, your probability will default to 0.5, or whatever number you want to default to, right? Suppose in case of words, the probability of observing a word is 1 by n, basically any random word from the corpus. So if this was word, right? So this is the distribution of word by total words, the probability of a word. Then to make sure that it doesn't go to 0 when the number of words goes to 0, I can actually say that this is nothing but 1 by n in the numerator, plus n by n in the denominator, right? So this will say that this is nw plus 1 by n n, and n plus 1, right? So what happens is that if this is 0, then the probability of w is 1 by n. It means you are saying that, okay, it is like, it is not that unlikely. It is just 1 by the number of words, and this is a very good assumption, right? So, and we will see that this, whatever we are doing, has a very, very close relation to what we do in actual modeling, right? So this has a very, very close theoretical backing, right? But before going into that, I'll talk about the other way of doing things, which is where things get much more interesting, and this is where theta is a random variable, and this is where Bayes theorem, and we call this the Bayesian approach. And if you look at the lecture, the actual lecture from there's always a very large debate. So the one that we just which is called the frequentist approach, right? And what we're trying to say, go into is called the Bayesian approach. So there's a lot of debate between the frequentist and the and the Bayesian statisticians. But we'll see. So what the Bayesian way talks about is the Bayesian way says that the probability of my data is a function given theta. So I'm trying to estimate this, right? So I'm not here. Theta is not a parameter. Theta is actually a distribution, right? And to do that, what we need is something. So so basically, what I want to look at is P of theta given t. That means what is the probability of getting a particular theta given the data distribution. So I have some data distribution. It given me some data distribution. I want to estimate theta. So I want to look at this one, and you will see. So the previous thing, right? So previous likelihood we estimated is parameters by theta, and we had that that binomial expression for this. Now we will say what is the probability of this. This is my likelihood. So if in Bayesian statistics, like P of A given B is nothing but P of B, P of B given A, and then P of V, right? So this is my usual Bayesian theorem. So in this case, P of theta given t is nothing but P of theta. Sorry, this P of A, right? So P of theta, P of d given theta, and then P of t, right? And this is very important. This is called the likelihood. This is also called likelihood, and this is a very close relation between these two, right? This is basically the same. We have to model the same likelihood, and P of theta is up to you. You can make an assumption there. So in previous case, you made an assumption that the coin toss is fair. So in that case, you can say P of theta is 0.5. And what happens in that case is that if you don't have any data, you will say my probability my probability of seeing ahead is 0.5. So if I don't have any data, I will fall back to my prior belief. If I have some if I have some data, I will fine tune my prior belief with the data, and that is called the posterior, right? So in Bayesian way, we have this prior and the posterior. So prior is what my belief about the world is. Once I start collecting my data, either my belief stays because the data is according to my belief, or my belief changes, and my posterior is how my data changes my belief, right? And that's a very elegant way, I would say, of thinking about it. I'm not in favor of either frequentist or Bayesian, but I'm saying there's a very elegant way because it's a very holistic way of talking about things, rather than saying, okay, whatever the data tells me, I'll just assume that, and then I'll make some tweaks. That is not a bad way, I'm saying, but that's not like a very like anyone who like likes this kind of more like theoretical or viewpoint. Yeah, that is very good if you're not trying to make an assumption and things like that. Here you have to make assumptions, but this gives you a much more granular control over your estimation, right? So and again, like so for binomial distribution, we talk about, we estimate a beta distribution. Beta distribution is distribution of a probability. So if I want to if I want to model the if I want to model a probability value, like probability of heads or probability of a particular event, then beta distribution is good in modeling those things, right? So I can always take the distribution to see what is the uncertainty about a particular estimation or particular outcome, or particular Bernoulli outcome. So probability of it is a Bernoulli distribution. So beta distribution usually comes in when we have estimation around that, or, sorry, so beta distribution comes in when we have a uncertain estimation of a binomial distribution, not Bernoulli, but binomial distribution. And this is basically the setup. And this is my prior. So I say my prior is based on beta distribution, and the posterior is based on binomial distribution. And you see this has a similar form, like there is basically so basically if you multiply this one, you will still get NH because that many heads you have, but you have this alpha plus one, and you have the beta minus one term just added to your n heads and n tails, right? So this can be my prior. So this is my prior, and this is my likelihood. And based on this likelihood, my posterior will get shifted towards my likelihood. Right? So, and the likelihood is basically coming from the data. So again, like what we'll say is that we have some data, and we'll try to. So basically, this is called maximum a posteriori probability estimation. This is called MAP, and you will see this in a lot of scenarios that MAP also comes up. And what it's saying is that I have to take theta such that this posterior is maximized, and this is basically a function of the likelihood and my prior, and I can get rid of this, and then because I want only to figure out the numerator, and this is only a function of theta. The denominator is not a function of theta, so I can get rid of that, and then I take the log to kind of make my life in terms of sum, and then I have these results, and suddenly I land into this kind of a this kind of a equation, which interestingly, which is very similar. So in case of the maximum likelihood estimate, we got nh plus some value by n h plus nt by by the normalizing factor, say. So in this case, it's very similar to that, right? So you are getting alpha and then you're getting beta plus alpha minus 2, right? So you are getting similar things with the smoothing that we discussed. So both of them actually land onto similar kind of distribution or similar kind of estimation. So both of them reaches the same answer, but have very different viewpoint or very different ways of reaching that. Now you would be wondering, why does that matter? Why is it like important, right? Why can't I? My life was simple before this. I used to throw in data to my loss function, and I get results. So why should I care about this, right? So and um, I would kind of go so if you think about this, the first one, the first way you are trying to model p of y given x, and you are parameterizing by theta. The second one, you are trying to get p of x given y. You're trying to model this one, right? You're trying to model this function, and there's a lot of difference between these two functions, right? So you are trying to, in one, you are, this is your likelihood. In the other one, this is your likelihood. There's a lot of difference between these two. uh, like and the reason is, so in one, I am actually doing the joint distribution of p of, in this one I'm doing just p of y given x. I'm interested in only p of y given x, and so given a x, my model can tell whether this is the right class or not, and it works. I mean, that's what I wanted to, I set out, that is what I wanted to do, right? There's nothing wrong in that. But the other way, you have to figure out this joint distribution, then only you can figure out p of y given x, right? So why? Because in the second one, p of y given x is nothing but the p of x y and p of x, right? So this is what you write as p of x given y and p of y, right? So this is what we usually write like this, and you have to model this entire thing. And but there's a boon in this, right? So if you can model p of x given y together, you can actually get access to p of x given y, right? Or actually you can take this and you can marginalize across all y, and you can get access to p of x, right? And now we are in that framework where we can generate data. We can actually generate data. So this is that framework. So because like I am I can model the full distribution, the joint distribution. I can generate data. So that's why it's called a generative framework, right? Because it has the power to generate new data, right? The other one, which is just modeling p of y given x, that is called a discriminative framework, right? So the only thing is that here I can directly estimate. I can throw in that parameters and estimate that parameter is whatever loss function I want, and I can get that model working. In this case, you're saying no. I don't want to do that. First, I have a prior belief about my y. Then I have to calculate my likelihood. Then I will reach my this is my posterior, and then only I can give you the answer. So in that case, you go into that step. But in hindsight, you have this great capability of generating data, right? And this is the framework. So right now, if you look at deep learning, all of the generative models, in the hindsight, what they are learning is how to generate the data, right? So previously, we used to have some text, and we care about generating the label like spam or not spam or sentiment. So we would build this classifier, will text feature, go to the classifier, it will predict something. Now the lot of generative models, they kind of generate p of xi given x1 to xi. This is like if I look at all the words previously, what is my next word, right? So this learns basically p of x. I'm learning that p of x, and you'll see that then this model gets trained to p of x, y given x, because if you can model p of x, you can model the feature better. So this kind of I'm not drawing the absolute mathematical equivalence. Don't take this as an absolute theoretical equivalence of both of this, but the generative framework actually comes from this kind of a thinking that to kind of generate data, I can only generate data if I can model the joint distribution. Otherwise, I can't. Any of the discriminative thing, I cannot, right? And so this was pioneered by, you will see that the first thing that pioneered it was something called autoencoder, variation autoencoder. We'll come to those kind of things in later classes. But those are things that pioneered it. And all of those things, autoencoder is a feature encoder. It is used to compress feature. Basically, it takes the same input and output the same value, right? So the input and output are same for autoencoder. The same, like you are taking the feature, you're trying to regenerate the same. You're taking an image, you're trying to regenerate the same image. So in that case, you're basically learning the P of X distribution. And from then you can create features that can help you learn the P of Y given X distribution. If you learn P of X, you can represent P of X, then you can actually learn P of Y given X from there. So in that case, we have this concept of latent variable and things like that. I'll not go into that, but basically you will learn a latent distribution, and you take the latent distribution, and then you learn then you take the latent distribution for your classification task. So I'm not going to that today, but I would say that is a very interesting framework that basically comes from here, or has a lot of backing from some of what we are looking at today, right? So the true Bayesian approach, I mean, whatever we saw is like, so basically what we are trying to do is that we want to get this one, so P of Y given this data and this X, and what we want to do is that we want to estimate this one, right? So basically this is taking over all the thetas, the P of Y and theta given D and X, and now you can say, okay, P of, so Y given theta, and then this, so this is my this is my input, and this is my parameter. So I'm first estimating P of Y given theta and D and X, and then I'm saying what is my the given this one, right? So my theta is basically is a function of D. So and then I'm estimating Y given this theta, and somehow this is integrating over all of such thetas, right? And usually, like, this is feasible for simple distribution, but for any arbitrary distribution is extremely hard. So ideally, like, the true Bayesian approach is not feasible to compute. So usually we'll see that we either make some assumptions, or we fall back to the MLE law. So most of the times we either take this, we never take this true Bayesian approach unless things are as simple as coin toss, right? Other than that, it's very hard to kind of estimate all of this. Right? So that's kind of the premise. Any question on this one? Yeah. Whoever raised your hand, go ahead.
I had one question with respect to the frequentist approach that you mentioned. So I think you said something like the maximum probability of getting a heads. I wasn't very clear with that part. Can you please repeat?
So basically, like, what you are trying to estimate is not maximum probability of getting a head, but basically what I want to model is this thing, the likelihood, right? What is the probability of observing my data given theta is my parameter, right? So what you're trying to estimate theta, right? So if my theta here is the probability of head, right? If I say probability of head, right, and then I get 50, in 10 coin toss I get 8 tails and 2 heads. That is that matching my data?
No.
No, right? So basically then theta will try to get to that value which will maximize the likelihood of my data. That means whatever observed will try to fit that, right? If it has observed 5 heads in 10 tails, in 10 heads, in 10 coin toss, then it will be close to 0.5, right? So basically we are trying to maximize the probability of that likelihood. That okay, what is this likelihood? Or what is the probability of observing that data given, or not given, but parameterized by that theta. I have estimated some theta. Is that the right, that fits my observation? If not, then go back and change my observation, change my estimation, and you are going to do that, right? So what is the estimation that explains my distribution? Does that make sense?
Okay. Yeah. Yeah.
Yeah. So like the maximum likelihood estimate is, if you think about it, the maximum likelihood estimate is basically I am learning this probability of y given x, and here the probability is parameterized by theta. There is a parameter theta I. So from the loss function and whatever we estimate this parameter and we assume that is this. In case of discriminative model, we are saying what is the probability of y, and I am also getting this theta, right? Given I have my x, right, which is my features, right? So this is what I'm trying to estimate, and so now the question is, how do I do this, right? So this is basically nothing but p of y given theta comma x, and then p of theta comma given x, right? So this is how I can break it. So the difference between these two is this directly modeling the p of y given x, right? But in this case, we're not modeling that. We're modeling a joint distribution of the theta and x, and then we are trying to, like answer this question. So if you see that, to get here, I need to basically, go over all theta, and then I will get p of y given x. So p of y given x is nothing but I'll have to integrate over all the thetas to get there. And that is what the Bayesian approach is, right? So the Bayesian approach, in some sense, what you are saying is that basically I know I have some prior belief of what theta can be, because suppose like you're in this coin toss, or you have a spam email, or so from the historically, like 10% of the email is spam. So p of y given x, my prior belief is 10%. This is my prior belief, right? But then I also have I also have a posterior, which will or like then what I will say is that okay, then I will try to model that what is my, like what is the likelihood that will happen, right? So what is the what is my theta? So whatever I'm trying to estimate, right, what is that theta given I have y and x, right? So that I'll try to estimate from this, that, so that I'll calculate the likelihood, like, so sorry, I think I jumbled up this one. So what I'll say is that I have some initial distribution of p of y given x, and then what I will try to do is that this is basically what I want to estimate from my theta, and then I will say, okay, what is the likelihood here, right? So how can I generate a spam email from my distribution? So and then I'm saying that okay, so I have both of them. I have the likelihood, and I have the the prior, which I assume, and then I'm trying to compute the posterior from that, right? So I'm computing the posterior. So this is not y given x; it's basically probability of y. So then I'm trying to calculate the posterior from these two values, right? And that is what my whole thesis is. That first I will start with an assumption. So first I will go here, and I'll say, uh, in this case, like, so I'll start with, I'm trying to estimate p of y given d and x, right? So this is what I want to do, and I'm breaking this down into the first thing that I'm doing. So first thing that I have is a prior, and this prior is what I believe it to be. So this is my belief of prior belief, and then given the data, given this d and x, I'm trying to trying to estimate this, right? So that this is my likelihood, right? So this is like, can I generate a new spanning event, right? So that's what it's saying, right? So that is the whole thesis of this one. So that is a difference, right? So I have to learn both here, and I, because I have a prior, my, even if I don't have much data, I can still give you some some viable results. But as I have more and more data, my estimation will get better. But again, like, this is very hard, because now you have to go through this likelihood process, right? Which is hard, right? Previously, you can directly go into modeling P of y given x, and we saw that you assume some parametric form, and then all you have to do is take the loss and minimize that loss. In this case, you don't have a loss right now, right? So because why you don't have a loss? Because you have a prior belief, then you are formulating the likelihood. Then based on the likelihood, you can't, it is not one theta, you have to integrate over all the thetas that you can think about, right? And that all the theta that exists, because theta is now a probability distribution, you have to take a integration over all those thetas. And the problem is that the distribution space might be so large that this integration, you can't do it numerically, right? And then you are stuck, right? So that's the problem with this, with this kind of approach, right? So but this will give you a much better sense, because you're integrating all the theta, and you're taking an average over all the theta. So your estimation will be much accurate. If you can actually do it, it will be much more accurate than MLE, provided you have the data and you have the computation power. Does it make sense? What is the difference? Okay, makes sense. So with this, I will go into one thing that that probably is very interesting. So so let's think about linear regression, right? So let's think about linear regression. Sorry, any question before we go to this one? So let's take this as an example. I think it might be easier to take this as an example. Uh, so I don't think like we will be able to go to the example where we're estimating all of this with Bayesian, because that is a lot of times a more difficult problem. But let's try this out. Let's take the discriminative approach or discriminative approach in case of linear regression, right? So in linear regression, you will see that usually we make an assumption. So usually you will see that we will say that in linear regression, what we'll say is that like we have this y, and I'm trying to estimate this one, and so why do we get this loss function as a choice, right? Is that the loss function is something that we derive, or is something that is backed by from theory, right? So in linear distribution, all the points are IID. We'll see these are IIDs, and we assume that all the loss or the error. So basically, I am saying y is a function of my theta, like h of theta x, and plus some epsilon I. This is basically a noise, which I can't estimate with my estimator. So there's always some error in my estimation, and that error, I'm saying that error is nothing but random noise. It is distributed with mean zero and a normal distribution and some variance. And I can model that variance. I can say that the probability of this error is nothing but it is a normal distribution. And if that is the case, if this is the case, then I can say then this is basically P of y given h of theta xi, each parameter like this one follows a normal distribution. I can say this because if this is distributed normally, this is also distributed normally. P of y given is also distributed normally, and right. So this is basically P of distribution given y x parameters by theta, not given theta. Right? P of y given is not given theta, but it is basically parameterized by theta. Right? So and so we do not condition on x. So these are very important things. So if you condition on x, then x becomes then we go back to the Bayesian approach. This is very fundamental. Like you're not understanding why that theta is what is the difference between theta being a random variable. I just say that go and brush up some basic like conditional distribution and things like that. In one case, when I say something is conditioned on this, that has to be a probability distribution. And if it's a probability distribution, now estimating that probability distribution is a different challenge than saying that it's a parameter. And parameter can be estimated using, like optimization problem. Yes, distribution can be also, but the whole framework is very different. It's not a parameter anymore. So then I can say this is distributed with this. And so when you go and study, there are 7 assumptions of linear regression, and all these 7 assumptions comes from this thing because it's IID, and we are making this assumption on the error, right? So we are making an assumption that all the error is with 0 mean. You see there is something called heteroscedasticity or something like that of the error, and that comes because my error has to be 0. If it's not 0, then I can't make this assumption. So only the modeling assumption I'm making the assumption that this is distributed with 0 mean and sigma, the constant variance, right? Like a pre-known variance. And if that is not true, if my variance is changing, then all these assumptions will fall through. So now what is there? So if we go to this MLE estimate, so this is my likelihood, and I have endpoint. So the likelihood would be a product because each of these are independent in nature. Because these are independent, my likelihood is a product. If it is not independent, it is not a product. If it is not independent, each of the points is not independent. Only because it is independent, each of the probabilities are multiplicative in nature. Each of the points, the probability of y given x is multiplicative in nature. Again, see the assumption of IID coming in so handy. If this is not true, you can't model this. And then you go to this, that okay, I can, this is my, this is my likelihood. Then I take the log of the likelihood, and then something very interesting happened. This is my log of the likelihood, and maximizing my log of the likelihood is same as maximizing my this one. So this is the trick of converting something which is non-convex to a convex. I say, and if we get a chance to study SVM, we'll see the same thing happening. We will see that we end up with a non-convex function, and then we say, wait, maximizing this non-convex function is also maximizing another convex function. So in this case, we said, okay, maximizing this is nothing but maximum. So if I want to maximize this, I need to maximize this one. Or sorry, I want to minimize this one. If I want to maximize this, because these are exponential, like, so this is a log of sum, the only way I can do it is I can minimize this one. And the way I can minimize this one is so this is where the natural, this comes into the natural, mean square error or the ordinary least square. You see that this comes into the mean square error, the loss function. And this is not by just by chance. It's because we made that assumption of IID. Similarly, if I go to logistic regression, similarly, like you will see that in logistic regression, as you all know, that my parameter is basically, in case of linear regression, y is equal to theta transpose x. In case of logistic regression, y is nothing but 1 by 1 plus the sigmoid of theta transpose x. I'm taking a sigmoid transformation on top of it. That's the difference between a linear logistic regression. But because my values has to be between 0 and 1. Again, like if I think from probability standpoint, in logistic regression, my prediction follows Bernoulli distribution. So P of y given x and theta is nothing but my classifier, the what my classifier estimate. P of y equal to 0 is 1 minus what it estimate. So and I can write it in the compact form. If y equal to 1, then I have this is my estimate. If y equal to 0, this is my estimate, right? And I can write this as my likelihood. Again, if I have n independent sample, I can write this as a product, and all this becomes product. Then I take the log likelihood, and we as kind of we arrive at this one. Can you recognize what is this? What is this loss function? Can anyone recognize what is this loss function?
Entropy loss, right?
This cross entropy, this binary cross entropy loss, right? And the nice thing about this is, again, this is a convex function, right? This is a convex function. And this exercise why this is a convex function. So you have to convince yourself why this is convex. Right. So this is again a convex function, and then like what you do is that then I have to maximize this, and you will say, okay, what like I can go and maximize this function, and so how do you maximize? Like we can do this, right? We can use gradient descent, right? So basically, like we can say, okay, great. So let me take the direct derivative of this, and we get this one. right? So this function has some challenges. It is I would say it's not like so there's some condition on which it is convex. So you just read up on this. There's some kind of asymptotic nature to this function. So again, like we arrive at this function and we see that we arrive at the same loss function like that we started with, which is basically like the same update function, and that's kind of like the idea, right? So that's kind of again, like coming back to the same principle. We arrive at, so two things, right? One is that two things that you guys like probably have realized. One is that the reason why we use these laws, or a lot of these assumptions are not, or a lot of these things that we take for granted are not that simple. They comes from a very very well thought of kind of principles, right? It's not like, so that is this very very first principle way of approaching this, that why we are asking every time, why should I do this? So how should I estimate, right? Is this the right estimation, or should I estimate by some other ways, right? And then we are taking approach. Why is important? Maybe you're reaching the same conclusion that we started at the start. So we know this loss function at the start, right? So it's not that something we drastically change on the loss function side, but now we know why we have that loss function. And because you know why, you have an immense power to now tweak it. Because now if I say, can you use a different loss function? You know how to get a different loss function, right? Now you know how to create that convex function. You know what is the probability distribution, that what are you modeling. If you need the P of X data, you need a generative model. Now you can make the right choices to do that. Maybe it is not computationally feasible to do it, but you have that power to do that. And that gives a very, very flexible way of thinking about modeling. It's not like I have some data, so I model, getting some results, and then calculating all the accuracy and things like that. But you are doing very fundamental things where it is coming from. Your Python code will not change much, but now your interpretation of those will change. Now if you see something not converging, you know why, and what tweaks you can make. You can either play with the loss function, or you can play with the with the learning rate, and things like that. You know where are those knobs. So that's kind of that was my agenda for today. So I will go into something that probably will give you a better way to think about some of this. So let me share that. Can you guys see my screen? Can you see my screen?
No.
Okay, let me. Can you now see my screen?
Yes.
Let me share this. I don't know how to share this one. Yeah, these are small coding exercise that probably would be very helpful to. It is a starting point. It's not like something very revolutionary. But I think this would give you a way to tweak some of this, right? So, for example, play around with, maximum likelihood estimation, right? So, for example, here, I'm defining a coin estimator, and if I have some number of flips, then I say mean of number of flips. If I, then we can also do a map estimate, which is so you can actually I'm just trying to so you can actually do this map versus MLE versus map estimate from this, right? So this and you can play around with it, right? So you can make it like you can simulate, you can add more flavors to it. But this will give you what is the two different estimate, map versus MLE, right? So the other thing that I wanted to say is the beta distribution. The beta distribution is a very nice distribution to look at. So when you say alpha beta are basically you can think about your prior, how many prior toss you have seen, how many success. Alpha is the number of success, beta is the number of failure. So if my alpha is very large, you will see that the probability of getting ahead will move towards the right hand side. If my beta start increasing and it becomes say 10, then you see it start so if alpha is small, that means beta is very large. So this is basically the uncertainty about my estimation of the probability of head, right? And right, so basically like this what it will model. And then we have a maximum likelihood estimate, which is basically for Gaussian estimator, I'm just with some prior so there's a map and so same MLE for instead of binomial this one, and you can change the prior, and you can then you can change this one. So I can change the prior, and I can see how my this distribution changes. And so one thing that I have given here is so one thing that I didn't cover in all of this is so when you come from so let me kind of go and see if that is there in the notes. Yeah. So if I kind of go from this direction, right? So so there are two things in linear regression that we should understand. One is that we already saw how we reach the maximum likelihood estimate, but actually what we are doing, right? So actually what we are trying to do is so there is a like a I would say there is a do you remember like when you have ax equal to b? This was like something which is taught in every 10 plus, or like not in 10 plus 2 but in colleges. We said that if there is an exact solution, then the rank of this matrix A is full rank, right? If there are multiple solution, then this will be the rank is lower, right? uh, do you remember some of this, like how the rank of the matrix actually determine how many solutions you have, and something about column space and null space? Do you remember?
Yes.
Right. So one way to think about linear regression is also from that space. Again, like linear algebra, calculus, probability, all converging to the same space. So the thing is that if this is your column space, think about the matrix, this is your column space. You are trying to find the equation which gives you this y given x, and you want to find this a, right? And the problem is that this a might not lie here because there is no exact solution to your y. So your a might, so basically like then so from your x space, that is from your like here x is basically your a. So and your like so we have the estimator. So basically we can say X transpose W is equal to Y. This is what you're estimating. X is given. So in the same column space as X, your Y doesn't fall. Y falls in some other space. But what you are trying to do, you're trying to find the closest approximation of Y in that space. And that closest thing is what is determined by this least square estimate, right? So how do we know that that is the case? Because like if X was invertible, then I could have an exact solution of Y. I could have exact solution of Y, right? Uh, but since X is not invertible, why it is not invertible? Because usually we have 10 features and 10,000 rows. This is not a square matrix to start with. So of course the rank cannot be more than something, right? So that's given, right? The rank of that matrix cannot be more than something. That's one. Second thing, we'll also realize that if I have 10 sample at 1,000 feature, this is not again like this is not I can't take I cannot go to the columns because there's too many features, right? So usually like the feature should be less than the number of samples. Again, like that is again following from this principle of finding or the equation, solving an equation. But the thing is that since I can't find an exact solution, I will find the closest approximation to my solution, and then I will estimate that with this t-square. Right? So these are very nice geometric way of thinking about all of this. That what we are doing basically in that column space of X, whatever my feature space is, I'm trying to find a closest linear combination of those values. And what I'm trying to find is Y, which is the closest. If Y is in that space, you have an exact solution, which is never the case, right? So that is one way to think about linear regression. So we'll see that most of the time in linear regression, the solution is basically a pseudo inverse. It's called a pseudo inverse. So this guarantees that your X has an inverse, and then you're estimating by this. So all through all of this, you will actually reach. So what I wanted to show you is the map estimate. So this probably will understand the map estimate a bit more. So we know that uh, right? So we know that, so we have a prior. So we assume the prior, that means the prior of my estimate, the prior of my parameters are normally distributed. In linear regression, I'm assuming that my prior, that means my thetas or whatever my W weights are, they're all normally distributed. So my prior of is basically something which has some zero mean and some value. So basically, we say that our initial parameters are random. We start with random. So we are saying that the same thing. Initially, we don't have estimate. I say it's a random combination of weights. So the W is random. From that, we kind of go and estimate W, right? So initially we said that this, again, like I'm assuming like initially my weights are random, and then I'm trying to. So what I'm trying to do, So I have a likely, I have a likelihood. I have a like this is my prior, and this is my likelihood. That means what is the probability that I have seen the data given this parameter, given given that parameter, does that parameter fits my data, whatever I observe, right? And from this I can actually estimate that this is nothing but doing so this is basically and you see that this there is a this term plus this W transpose W tram. So usually like you will see that uh, uh, like so I have two terms. One is so in this MLE, right? So so how do we reach this this R? So we said that like I have these values, and then Y is nothing but this then we have this one, and then this my difference between, so this is my R. So I have R transpose R, I have R transpose R, and I have something which is very interesting. This I didn't get in the MLE. In the MLE estimate, I in the MLE estimate, I directly got Y. So R is Y WX, and I'm saying R transpose R is this minus this. Basically, this is my loss. So this is nothing but WX square, basically, right? So this is my loss. And then I'm getting a very interesting term that I didn't get. And can you see what is this? Can anyone tell me what is this? In the loss, in the log likelihood or in the loss, I am getting a function of this, that my loss, plus W transpose W. What is this? Can someone tell me what is this? If I say that my loss is this plus W square, what kind of loss is this? I have the actual loss, which is predicted minus, sorry, actual minus predicted, plus I have some function of the parameter. What is this?
Regularization.
This regularization, right? So you know why the regulation comes, right? Because you have some assumption, right, of the parameter, right? So again, coming from the probabilistic framework, we're actually arriving at the regulation framework, right? If Emily was there, whatever from the data you will believe, right? But now you're saying, no, no, I don't want to believe the data. So I want to also put some guardrail that I don't overfit the model. And the reason that is coming, because if you have too many less samples or too many parameters, you are going to say what the parameter is going to say. But then you want to reduce that noise, and that noise is a function of your parameter. And again, it is squared because you assume the normal distribution of your parameter. If you have some different assumption, like that's why the lasso one. So this reach and this lasso, which is L1. This is in L1 we have a very different distribution assumption of W, and then that's where this is all coming from, right? So again, like just trying to so because I have in the notebook lasso and reach, so actually you can actually arrive at all of this. So you can either use scikit-learn. I have also given a code where you can actually do actually write your own linear regression. So write your own linear regression and or write your own logistic regression. So all this is given. Feel free to play around with this code and get some interesting results. So I'll not explain the code. So I think that's something that uh, I'll give you the exercise around this code. So this exercise will be around this code. We're out of time. So I'll stop here. Uh, yeah, probably we'll have some in the next class. We'll have some time to start with the question and answer on this. But as a follow-up, you will get all the materials, and I need a couple of volunteers to help me transcribe or put notes to this course, or even manage the repository and things like that. If you are interested, just message me on Discord. And once the assignment is there, or so I'll just put it on your GitHub. And this is a good chance to you do some project hands-on thing on GitHub. So this is starting, but as we go into more and more weeks, I think we will go into more and more like real life problem. But this is like a theoretical backing. Now, since we have the theoretical backing, now I think we will go a long way without visiting any of this, and we more focus on practical problems like practical Kaggle problems and things like that going forward. There'll be another set of theory probably if we go to XGBoost and all these things, that area, and then there'll be theory when we go to deep learning and those kind of areas. But most of the next set of classes would be less theory but more practice. So yeah, so that's kind of I want to stop here. And yeah, let me know if there is any feedback. How can we do it better? Let me know. And yeah, and hopefully like you had learned a lot in this session. I'll try to upload like I have usually like very difficult schedule for me. So I if there's some delay in uploading the video and things like that, don't panic. I'll do it as soon as I get some time. Um, cool. I think the next topic of the session, I will probably again continue in the supervised learning part. So I think what I'm planning is I'll go down the supervised learning till XGBoost, and then we'll take unsupervised, and then we'll go to deep learning. And finally, if there is time, and we, we have enough attendance towards the end, so we will go to RL and things like that later. So that's kind of the idea. I don't know how much specialization in deep learning we can do. I probably classical deep learning, a lot of NLP. I don't know whether we'll get time to do computer vision and things like that, but mostly, that's what I'm planning. So thanks everyone. I need to drop, and let me know if you have any question on otherwise. Shravani, it might be difficult, like all the sharing 30, because probably like the way I'm thinking is that maybe not every 2 week I might be able to do this. If I'm not able to do this, I will fill in with something else so that you still like learn. Probably someone else will take the session or something like that. So I don't know whether I'll be able to take all the 30 weeks. I will try to take most of it. That I can promise. Okay. Thanks again, everyone. Yeah.